Hello, continuing with our work in the conjugate root theorem, we have this question here. If 2 minus 3i is a root of this, where a and b are real, find a and b and the other roots. Key fact that I see here, a and b are real, and the coefficients that I am able to clearly see that are given to us directly are also real. That allows me to use the conjugate root theorem, and only when I know that I have a and b real, or all of my coefficients real, can I use my conjugate root theorem. So that's going to help me to find a and b and the other roots. So I know one of the roots, and I can see that it's a complex number. I can see that this is a cubic equation, so it is going to have 3 roots. Now, because it has one complex root and they come in pairs, that tells me either I'm going to have another complex root, the conjugate of this one, complex conjugate of this one, and then I must have a real root. Why must the third root be real? Because it doesn't come in a pair. There's only one more of them, and only real roots could come in ones, because it was a third complex root, it would have to have its conjugate, and I'd end up with 4 roots. So a cubic is going to have 3 roots. I know that one of them is complex, so I'm going to get a pair of complex roots and one real root. So let's jump into this and see what we get. If I know that I have z is equal to 2 minus 3i, and I know and a and b are real, therefore z is equal to 2 plus 3i must also be a solution. Again, this is the complex conjugate, this is z bar. So that must also be a root. So now I have 2 of my 3 roots for very little work. And this is going to allow me to multiply these factors together, and I'm going to end up with a quadratic. I'm going to end up with a quadratic that I can divide into my cubic. Very much the same style of thing as we would have done for the factor theorem in pure algebra before we were dealing with complex numbers. So once we deal with this bit about the conjugate root theorem in the beginning, this becomes basically a factor theorem type question. It just looks a bit funny because we have complex numbers involved. But if we know these roots, we can use the factor theorem to find our factors, because if we rearrange this to be equal to 0, we therefore have the factors. So let's rearrange these, and I'll end up with z minus 2 plus 3i is equal to 0. This is one of my factors, and z minus 2 minus 3i is equal to 0. This is another one of my factors. I've rearranged these two to get them equal to 0. These are now my 2 factors that I'm going to multiply together to get the quadratic factor of my cubic, and then I'm going to use that to get my remaining factor and find the values of a and b. So I'm going to multiply my factors together. Z minus 2 plus 3i and z minus 2 minus 3i. I'm going to multiply these out and come back to you. So we've multiplied out our brackets, standard algebraic multiplication, nothing unusual in it. And now we have to gather up our like terms, and putting different symbols underneath each of our different styles of object can be very helpful in this type of situation. I can see lots of things that are going to sum to 0. And I see an I squared here I can turn into a minus 1. And I have minus 4z. This sums to 0. That's dealt with. Plus 4. That sums to 0. That sums to 0. Minus 9. And minus 1. So I end up with z minus z squared, my apologies, minus 4z plus 13. And this is our quadratic factor of our cubic equation. Now, there are two methods that we can use to move forward from here. One is long division, and the other one is factorization. And I'm going to go through both with you. Both are totally acceptable, and both definitely have their uses. So this is my quadratic factor that I have found from having roots, using the factor theorem to get my factors, multiplying my factors to get the quadratic factor, and now we're going to start with long division as our first way of doing this, and then we'll look at another way of approaching the problem. Az squared is bz minus 65. So z squared, highest power into highest power, z squared into z cubed goes z times. I would expect to end up with a linear factor here, so that is good. Then multiply my result into all of these. I end up with z cubed minus 4z squared plus 13z, plus 13z even. Next step is subtract. If I subtract the negative, it's the same thing as adding. And I obviously get 0 there. I get, these are both z squared, so I'm going to take the common factor of z squared. I'm going to say in brackets I have a plus 4 z squared, and I have common factor of z, so I'm going to open a bracket and I have b minus 13z. b minus 13z, and I bring down 65, minus 65. Now the whole process starts again, and I have z squared goes into a plus 4 times z squared, a plus 4 times. And then I multiply in. Pardon. Minus 4 on a plus 4 times z, and 13 on a plus 4. Next step is subtract. Subtracting a negative is the same as adding. And this obviously sums to 0, but these two must sum to 0 as well, because I know that this is a factor of this. Therefore, I can say that b minus 13 plus 4 times a plus 4 is equal to 0. And I also know that minus 65 minus 13 on a plus 4 is equal to 0. Minus 65 minus 13 on a plus 4 is equal to 0. And I can simplify both of these down. And I'm going to rewrite them in columns for us now. So I work this down and I run into a simplified equation with a and b. I then try the other equation to end up with something simplified, and I actually get the value for a. So now I'm able to sub that in up here, and I get in 4 by minus 9 plus b plus 3 is equal to 0. When I rearrange that, I get b is equal to plus 33. So I now have my values for a and b. I can use that to find my final root. Z plus a plus 4 was my final root. I now know the value of a. So z plus minus 9 plus 4, z minus 5 is my final factor, and I know that to turn that into a root, I'd set that equal to 0, and z is equal to 5, and it's a real number, as we were expecting, because it doesn't have a pair. It's the third root. Now, if we were to do this long division step using factorization, what we would do is open up some brackets. We have our quadratic factor set up here. So this is the question done. It's perfectly fine. This step can be done using factorization, and that's what I'm going to show you right now. So we have some linear factor multiplied by our squared factor must give us our cubic. Z cubed plus AZ squared plus BZ minus 65. So this must equal this. So there's a few things I can very easily figure out. The cubed term is going to be by x, z. The cubed term is going to be just z, because z by z squared will give me z cubed. There's no coefficient in front of this that I need to worry about. It's just 1. And then the number on the end, well, if I multiply the second number here by the last number or in this bracket here, I must get minus 65. So if this is 13, what do I need to multiply by in order to end up with minus 65? Well, I can just do it by division if I'm not sure, but I will end up, so I could have minus 65 divided by 13 would give me the number that would necessarily be in here, and it is going to be minus 5. So that gives me my third factor a little bit quicker than this method. But then how are we going to use this to find a and b? Well, I'm going to multiply out these brackets and then equate coefficients. So I'm going to multiply out these brackets now, and then we'll equate coefficients to get a and b. So when I've multiplied out my terms, I see that at the equating coefficients, I have a 1 in front of my z cubes and a minus 65 at the end. This is good. This indicates I haven't made a mistake. I have a in front of z squared and a and minus 9 in front of z squared. So a must be equal to minus 9, and b must be the same as the coefficient in front of z, which is 33. So we can see both methods and how they work out to give us our needed solution. So again, the conjugate root theorem, very powerful theorem when combined with our factor theorem, where we have our roots, we turn them into factors, and that is going to give us an ability to build back up to the original equation. But it is critical that we are always very clear that this only works when we have real coefficients. If they are not real coefficients, we cannot use our conjugate root theorem. And that's what we need for now.